try to time it on the music. But as you can hear during the song, for some reason the ducking already works, so you can hear me moving around stuff and banging on things and I don't know. Weet ik het wel. And then the music ducks, but there's no actual sound here, so yeah. Good evening all. I'm still busy preparing all of this because I'm late. How are you doing? And I am very happy you've decided to join this stream. Hello, hello, says Dutchmaker. Let's see here. Jacco Wies liked. Very nice, thank you. And then looked like was gonna be testing tonight. Maybe some Magic Smoke. I actually responded to that with my alternate ego. And then Nigel Young asked a question. I'll get back to it in a little bit. Well, hello. Pepsi says 4 weeks till Christmas. Yes. Evening all, says Greg E. And then we have Ginger Dan. Howdy. Hello. Jacco Wies again. Music has started. AK Storm and Johnny Bergdahl is here. Nice. Yeah, Jacco says the music is going in and out a bit. Yeah, that's because I'm then banging on my desk and doing all kinds of stuff. So, yeah. The question of the night is, will BTC hit 100k during this stream or not? Wow, it's fluctuating that much? Damn. Well, I don't have any BTC, but I have ETHs. So Ethereum, let's see, Ethereum. Last 90 days, 12 months. Oh, Ethereum is getting a nice bump too. That's cool. Let's look at Chia. Yeah, no. Chia's dead. Oh well. Oh, I still need to turn the music down. There. That's a bit much. Oh, Mr. Tech Gadget says hello. Hello. And then we have Sebulwa. Thank you for the amazing videos you create. Through your videos, I've understood and learned a lot. Many thanks. Thank you for watching them. I appreciate that. So, let's see here. Okay, I think I'm almost done with cleaning up. There's a weird echo I'm hearing, but I'm not sure you guys are hearing that. The microphone's a little bit further away than usually. That's because there's just a lot of junk on my desk. But I think I have most things cleared up now, so that's good. Let's take a look at the drinks for today, because a good friend of mine, she scrounged up some weird-ass drinks again from I don't know where. So, first off, we have Coca-Cola. Oh, wait. Coca-Cola Wobbly. Coca-Cola Lima. So I guess that's, with citron, but then with lime. Interesting. And then there is Fanta Zero Sugar Framboise. So framboise, which is raspberry, I think, in English or American or whatever. Yeah, that's going to be interesting. What is this ringing sound I'm hearing? Let's move these away. Do I still hear it then? La la la. No, yeah, maybe. I don't know. It's faint echo from the room, but it's always been there. Well, let's move the microphone a little bit closer. There. Maybe that will fix it. I don't know. We'll see. Oh wait, why are we not in focus? Oh no, we're looking at the subject already. And you can look at the mess on my desk. Is this... Oh, this one is not ISO enough. There. I like to have that slightly blown out so all the details of the dark things are visible too. Nice. Okay. Now would be a good time to insert an ad. No, it's not. That's why it's turned off. Playing Satisfactory while watching Quinled. Perfect afternoon. Nice, Tim. I play Satisfactory with a friend of mine, and I've just made the whole nuclear power lineup. So we first have the uranium power cells, and I've just constructed everything. So now I'm getting plutonium power cells, and then of course I have to build nuclear reactors that run on the plutonium, and then I don't know what I'll do after that. But yeah, Satisfactory is cool. Are we going to have part 2 of testing some WLED controllers this year? Maybe. I still have some samples. You also provided some. So maybe we're going to do that. Maybe not. I don't know. I don't like bashing on products in that sense. I think it's good information still. But yeah, maybe. I don't know. I have to feel like it. So, right in the beginning, Nigel Young asked a question. Have you ever seen the WT32H ETH01? I have. They actually released that right after I released my Quinled ESP32 ABE, which I released for a very decent price. And then they decided to undercut the price, basically sell it below cost, to kind of try and conquer the market, and then slowly over the year they increased the price again after a lot of products started using it. So yeah, I know that controller. It's built very bare bone, and it has some issues. It doesn't have USB on it, for instance, and some other weird oddities I don't agree with. That's why I build things differently. To the LED strips, I got a couple of them with a bit strange power in. Is on pin header, no USB. Well, sure, mine you can power by USB or the pin header, but they don't have a USB port at all, so they kind of cheaped out with not having a USB to serial converter and stuff like that. So yeah, and I don't agree with that. I mean, sure, you can run without a USB to serial converter, but it's damn convenient that all of my boards have one on there. It's an extra cost, but yeah. If it breaks or you want to reflash it or whatever, you're kind of stuck with the controllers that don't have one. Or you have to, wire it up and extra hardware and extra hassle. So that's my opinion. Hey. Is there a light on that shouldn't be on? No, I think it's just because the bar is higher. Okay. Are we 60 FPSing? Yes. Good. So, what are you guys drinking? Well, I'm going to start with the Lima. So we have the Lima here. Or, I think I'm going to start with this one, because this one looks radical. Yeah, I'll start with this one. What? Okay, F4. It should be higher. Okay, this should be... There. Rivella Persic. Wow. Is that sugar-free? I didn't know that existed. Gotta love the sales at BTF Lighting. Just dropped $2,000. Wow. 2,000 New Zealand dollars. Damn. Okay. What do you think Pepsi drinks? I think I can make a guess there, Pepsi. Are you drinking Pepsi? When do you expect to have stock available for your controllers? David, we have stock available, just not in the US right now. They ran out very quickly, and customs basically held our shipment for 2 weeks and then sent it back. So that's why we ran out. Currently, in the plane, there is a big, huge-ass new shipment, and it should arrive within a few days. So in the US, there will be new stock in a few days or so. Almoedler Spritz. Okay. Sounds interesting. So yeah, I opened it, but I didn't drink it yet. Let's see. The whole background's blue. That is, I don't know. It's like there but not there, so the immediate taste isn't very immediate. But the aftertaste isn't very strong either, but certainly present. Yeah, interesting. Look at me here, rating a soda like a beer. Oh, I guess it's not a secret. It's Black Friday, so I finally bought a new monitor because, well, as I showed in the video, my LG OLED is dying for sure. Maybe not today or tomorrow, but it will die soon, and I'm losing pixels per day. So I bought a new QD OLED, one of those 32 inches, 4K, 230 hertz, la 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 la. Very nice. I'm still calibrating it a little bit because out of the box it's oversaturated and things like that, but it's pretty nice. New Octa brainboard and power 7 HC power board. Nice. Good. I've never seen this on YouTube before. They actually have a feature called the Ads Automator. Okay. Oh, I know what I'm hearing. There's a can. I sometimes drink Monster Energy, and I keep hearing a ringing from this direction, and it's likely this can. So let me put that away. There. That should stop it. You need a new PC. Running 4790 since 50. Yeah, 4790 is kind of long in the teeth now. Yeah, that fixed the ringing completely. Okay, cool. Yeah, no, I have a 5950X with I had a 3090, but I sold the 3090, and I now have a 4070 Ti Super, which is basically the same performance, but I was like, okay, let's sell the 3090 while it's still worth money, because it's a fast video card, it has 24 gigs of VRAM, and get a 4070 Ti Super, which will later go into this streaming PC, because starting from the 4070 Ti Super, it has a dual video encoder on there. So if you're building a streaming PC, you need a 4070 Ti Super or higher, because it has a dual NVENC encoder instead of a single one. Anyway, that's all video streaming stuff. So that's currently in my PC, but it's basically the same performance as my 3090. But when the 5090 or the 5080 comes out, I'll be buying one of those, and then the 4070 Ti Super or whatever can go to the streaming PC, and we can move all the hardware along nicely. You had some mojitos and then started soldering some WS2812s in 1010 package. Okay. Interesting. Right, I think it's time. Because I'm interested in what we'll see today. Now, today we're going to take a look at 2 or 3 things. We're going to take a look at this guy. This is a digital signal digital signal amplifier, as it says. So it takes in one digital signal over here, signal in, and then it outputs it to 8 different outputs over here. And it can actually take in data 1 and data 2, so if you have a clocked LED strip. And basically it should duplicate whatever comes in here to all these 8 outputs. And it has a large power connector, so it should also be able to give that power. Now it should be 5 to 24 volts, 5 volt TTL, so there's a level shifter in there. And it doesn't use a lot of power because, well, whatever is in there just doesn't use a lot of power. Now I want to take a look inside of this thing and figure out what they're actually doing, and then maybe we'll test it. And I have my my testing wire here. Let's see. So this is my 16 gauge, 10 meter or 32 feet 3-wire bundle testing cable that is strapped around my room, so it's not in a bundle. And maybe we'll do some scoping to see what the output from this thing looks like, and for instance, what the output from a Dig Octa looks like. Yeah? So that'd be interesting. So I think we're going to do that first. Now this is still a bit dull. There. Okay, better. And then I have two of these. So these are RGB-WW, wrong term, or RGB-WC, also wrong term, amplifiers. So what those are supposed to do, they're supposed to take analog PWM input, RGB, WW, and CW, so it's RGB CCT, and plus, and then you can add power in here and here on this one, right? So two power connectors, and it then amplifies and sends it out again. So you can extend an analog LED strip with a new power supply if it needs to be longer. And this guy is basically the same thing, just a little bit simpler, but they're two different types, right? I mean, yeah. So if we have time enough after looking at the digital one and testing that one, we'll also look at the analog ones, see how those are made, and then see how well those function. Because, for instance, the Quinled LED boards, by default, I'd say they send about 20 kilohertz PWM. Well, this one says high-speed amplifier. What does high-speed mean? Does that mean 1 kilohertz, 5, 10, 20, 50, 100? I don't know. So I also have my scope here on the desk. Hello, scope. Oh. And we might do some scoping on the data signals and the PWM signals and things like that. Oh no, I hate the feet on this thing. And test all kinds of stuff. Transistor level. You know what? Logic. Oh, TTL. Yeah. Okay. Yeah. So that's what we're going to do today. So first, we'll take a look at the digital one because that's interesting. Now, I'm me. So I want to open it up first and see what it actually does. Analog lights suck? What? Why? Analog lights are cool. Okay, more screws. I think my lights on the top aren't turned on enough, so let me turn those on more. Exactly. There. Whoa! And then I can turn this down a notch. Yes, that should be better. Good. Okay, now let's see if this comes apart. Yes. The housing is pretty nice. Okay. Oh, well, there's not a lot in here. So we have the power input. And, well, there's at least no fusing or anything like that to speak of, because the power input is directly connected to the power outputs. As you can see here, we have a little IC here, which I think is an LDO. Let me get my magnifying glass. I could take the microscope out, but I don't feel like it right now. Yeah, this looks like an LDO. We have some capacitors here and a resistor. And then we have two chips, 74HC245D. Okay, so those are the 74HC245Ds. Okay, so let's look up a data sheet for that. Let me turn this off. Let's see if I can share my browser with you guys. Let me see. Browser. 74.245D. Oh, no, wait a minute. 74 HC245D. Jesus. Sorry. It's an octal bus transceiver from Nexperia, or it could be from some other vendors actually. But let's take a look at this one. Let's first make sure my browser is actually fitting in my scene here. There. Yeah, that's good. Okay. Actually, let me change this a little bit. There. Okay. Let's download the datasheet. Okay, let's see here. So this is an octal transceiver, 3-state. Okay, yeah, that can work as a level shifter. Supply. Okay, so they're just going to supply 2 to 5 volts, and that's likely why the LDO is there, to make sure it always gets 5 volt. High noise immunity. Oh, bidirectional bus interface. Okay, well, you don't need that for LEDs, but that's fine. Okay, so we have the HC is CMOS level, and the HCT is TTL level. Now, CMOS level is generally referred to as 3.3 volt, and TTL is generally referred to as 5 volt. So, since we have the HC version here, it'll take 3.3 volt signals, and it'll make those whatever the supply voltage is, but in theory 5 volt, right? There's some ESD protection. Okay, yeah, so it has 8 inputs and then 8 outputs, and it's just a bus level shifter. Okay. Okay, yeah, you can set the direction. A is B, input, or Z. Z means it's nothing, or off state. Okay. Power supply. Yeah, so it's expecting 5 volt. And then the output level, the output voltage will be VCC, but the input voltage is also VCC. Interesting. Oh, right, okay. Yeah, this is what I was looking for. So a signal, a data signal, has a low, basically a 0, and a high, basically a 1. And a WS2812B signal, for instance, is 800 kilohertz, or 800 kilobit, and it says it can send zeros and ones that fast. And the WS2812B works with latching it high, latching it low, and stuff like that to basically send the data to the LEDs. And the high input level, when VCC is 4.5 volts, we don't have a 5 volt example, because we know the VCC for the chip is likely 5 volt. We can measure that in a minute. But then we need a minimum of 3. This is weird. How is the typical 2.4, but the minimal is higher than the typical? This datasheet's borked. This is also incorrect. What? Min. That makes no sense. What? Normally, you have a min, typical, and max. And then min would be 2 volt, typical would be 2.5 volt, and max would be 3 volt, because of tolerances in the chip, basically. But having a lower minimum than typical, yeah, that just doesn't make sense. Let's just look at the typical value for now. And no, that makes no sense. What? This is also wrong. I mean, the low-level input is when it detects 0. The minimum would be 1.35, and then the typical would be 2.1. I guess, I don't know. This data sheet's kind of odd. Yeah, min is min guaranteed, but min guaranteed should always be lower than typical, I'd say, Christian. Like over here, the high output level with a VCC of 4.5 is minimum 4.4, typical 4.5. That's logical. But this way around is very odd. Anyway, we can see the low input is 2.1, and I don't know which value. No, 1.35 makes more sense. And then the typical output is, check another manufacturer. Yeah, this is very confusing. Let's check here, because they have one from Toshiba. Okay, same chip, does the same thing. It's just from a different manufacturer. No, they do the same weird stuff. What? I don't understand. Let me look up something real quick. So this, for instance, is the level shifter I use on a lot of my boards. Here you see that the high level output voltage is minimum 4.4, typical 4.5, right? That makes sense. And the low output is like 0.1. Okay, I just don't understand. Toshiba looks better. Okay. Info. Oh, right. Okay, so this specifies VCC. So if you give the chip 4.5 volt, you need 3.15 volt to trigger a high input. That makes sense. And if you give the chip 4.5 volt, you need a low of 1.35 or lower. That also makes sense. Thank you. Fine. Great. Now, they don't specify 5 volt. And with this 3.15 with 4.5 volts, let's divide that real quick. 3.15 divided by 4.5 times 5. That means that this chip is not suitable for data signals without a level shifter. Because the high level input voltage would be 3.5 volt if the chip is getting 5 volt. So this chip is suitable for 5 volt LED data signals, as all LED data strips use. But if you're using an ESP32, which sends out 3.3 volt, it might work, but it's outside of official specifications, just like with LED strip. Okay, interesting. High level output voltage, so with 4.5 volt in, you're getting 4.4 or typical 4.5 volt out. That makes sense, right? So with 5 volt in, or using the LDO here on the board, if you have 12 or 24 volt in, you're getting 5 volt data signal out. That is not the TTL version. Oh. Is it different for the Toshiba? Right, so let's take a look at the earlier one. High level input voltage. But it says it for both. Yeah, this data sheet is just confusing. we're sticking with this one. It doesn't say a brand, I think. It does say a brand. Okay, well, I don't know. And let me try and show you the brand, because I don't recognize it to start. There. Is that Fairchild, maybe? Or maybe it is a Toshiba, I don't know. What's the logo for Toshiba? I guess we could look in Google. Fairchild, yeah. Okay, so... Okay, Fairchild. Semiconductor blot. Let's see if there's a datasheet here. I think so. Oh wait, this is very different. hate it when they don't just give you the PDF. Oh, Fujitsu, okay. Fujitsu. So, but Fujitsu, has that become Toshiba? I don't know, actually. Nexperia. That's the problem with a lot of these vendors making the same chip, but then not having the exact same specifications. It makes it very hard to find the right one. So I think the Toshiba is probably... No, it has to have Fujitsu. Okay, maybe this one? Now this is from onsemi. I hate this website. Just give me the data sheet. View it online, I guess. I don't know. Yeah, this is from onsemi. Okay, they also have a version. But it states the same thing. 4.5 is 3.15, so 5 volt is 3.5 volt. So I think the HC is not for CMOS level, so it's not suitable for 3.3 volt data signals. And probably the HCT from Nexperia. Okay, sure. Oh wait, we're TTL level? No, CMOS level. Wait, did I have CMOS and TTL reversed? I don't know. Thanks, Christian. Thanks for Googling. It's always hard during a live stream. Fairchild. Nexperia. Fairchild. NXP. Let's go for this one. Yeah, and then they have all these different versions, so then which one is it? Let's go with the cheapest one. This one. Fairchild is now part of onsemi. Anyway, so it can be any kind of chip. Nobody knows. I think it's an old Fairchild chip, which is now... Oh, wait, sorry. So here in the top, this is the Fairchild datasheet, but it's now from onsemi, so who knows. Anyway, this is the Fairchild one. 3-state, okay. Low power for the HCT, but we don't have the HCT. Let's see what this one says. Okay, so this one, but for which chip is this? Oh, this is for the HCT. We don't have the HCT. We have the HC. Oh, I typed T. Sorry, my bad. HC, Fairchild, Lithuania. Okay. Let's take the cheapest one. Yeah, HC245A. I don't know what A is. And then we're back. So I think the HCT stands for lower input levels. So it will work with 3.3 volt. And the HC needs 3.15 at 4.5 volt. Or as I just calculated, it needs 3.5 volt with a 5 volt input. 1984. So I stand by the fact that I think this chip is, or this board is suitable for 5 volt data signals, but not for 3.3 volt. Again, it might work, but you're running outside of specifications. Okay, anyway, let's get back to this thing itself, because what we can see here is we have the input terminals here, it also says it, and then we see the data lines, and they're just connected in parallel to all the chip inputs. See that? So they're basically just taking that single input and splitting it over all the 8 outputs or inputs of the chip, and then also the 8 outputs. It's kind of a very basic rudimentary way of doing it, but as long as the input data signal can deliver enough current, in theory it should work. So I see a lot of people also buying these to have more channels. It doesn't work that way. Your input signal will be split or multiplied 8 ways, and those 8 will always do the exact same thing. So you can't add more channels to your controller with that. It's just to have more of the same, basically. In some situations, that's fine, so that's good. But yeah, looking at the traces some more, we do have resistors on the outputs. I'm actually quite happy to see that. But what value resistor is that? 330. Wow. They have 33R resistors on the output. That's not bad. There is some kind of gunk here. Not sure what happened there. But yeah, these resistors are... can I zoom in? Oh, I can zoom in more. Okay. They are 330 resistors. So in theory, as long as you give this thing a decent input, you should be getting a decent output. Do we want to try that? I guess we want to try that, huh? Yeah, let's try that. Let's use the Dig Octa. I'm going to snip off some 3-wire here because I have that lying around. And I can use my Dig Octa, so that's nice. This is a good length. There. I need to strip it. Oh, it's over here. So I'm going to use some of this 16 gauge 3-wire cable. And on the other side, okay. Using Freedom units? Well, for cable, I'm used to it so much on the Discord server and in my videos that I've kind of adopted it, I guess. So let me show you the Dig Octa. Oh, no. Oh, there's an LED bar attached. Hold on. No, there's not. Okay. So here we have the Dig Octa. So let me unscrew the 10-meter cable. But we can test with that in a minute. And let's screw in data. And let's give it some power. Okay. So it has this big input terminal, but I believe it can also take power just from over here. Oh, wait, other way around. VCC and ground. Oh, you can't see that. So I'm just going to hook VCC and ground and DAT1. Yeah, it came from one of our Discord members, Joey, and it's on an LRS 600. It works quite well. I like it especially because then you can have the massive 3x10 gauge power wires. I have to verify VCC is on this side. Okay. A boulder the size of a small boulder? What? So, VCC. DAT1. Yeah, 10 gauge wire is nice in the barrier style terminals. And ground. Okay, and let's take one of my LED bars that I still have here and hook that up to an output. Hold on. Yep. Let's see where I need to put the wires. I think it'll go here. Okay, let me show you. So there's a mounting plate you can 3D print. You can then screw it into the sides of the LRS 600. And I use some nuts here with the default standoffs that are included. Those are M3. And then you can mount it like that. And it doesn't obstruct the fan. All the cables come out nicely. And you can make this awesome little cable show here. I don't have a link right now, but if you search for a Dig Octa mount on Thingiverse or something like that, you should be able to find it. So let's hook up an output. Let's hook up the other side. I don't know. I'm going to put this back real quick because otherwise I don't know what the cables are. So ground, VCC, and DAT1. So, okay, let's verify ground, DAT1, VCC, and the same on the other side. So now we can lose the cover again. Okay. The Dig Octa is in 33R mode. I would assume this also has a 33R on the input. Yes, it does. There are 2 resistors here on the input. So that should match up perfectly. Okay, let's put on the safety glasses. I've never turned this thing on. Oh. Who knows? Maybe it has a pink LED in there, Johnny. Who knows? I don't know. So, power. Okay, well that wasn't very spectacular at all. Okay. Let me check the IP for the Dig Octa. Let's see, 1010, okay. And let's have it do some rainbow. There. Okay. That seems to be working perfectly fine. Good. So on a short run, it works perfectly fine. And we are giving it a properly level shifted 5 volt data signal. So that kind of makes sense. Now I do want to measure what kind of voltage the LDO makes. That's just interesting for me from a board design perspective. Oh no, my multimeter wires are stuck. Okay. Because let me start the software. There. Okay, now you see the same measurements as I do. And let's see. What is coming in? 5.07 something. Okay. What is going out? Oh, that's a more drop than I would have expected, but let's see later with more current. And then let's see LDO. I think probably this tab. Ah. Bad LDO. Or maybe good. Huh. Maybe they used a 4.5 volt LDO on purpose. So, whatever is coming in, let's see, is this in? No. Is this in? No. But this is out, right? Let me check something. What? Why are these capacitors not measuring anything? Let me zoom you in. Hold on. So if they're smart, they might have used a 4.5 volt LDO instead of a 5 volt one. Let me try and find a voltage on one of these capacitors. There, 4.4 volt. But that is that the input, the output? 4.4. Oh, wait, there's a diode here. Ah. 5 point whatever is coming in. And it's making it 4 point... Oh. Interesting. So maybe they weren't smart. It just happened to work that way. So we have 5 volt coming in. But it's becoming 4.5 volt or 4.4 something because of the diode. And then they're putting it into these chips. Or they have an LDO, but I think the input of the LDO will be the same as the output in this case. Let me check. See if I can find that. No. That's in or out, I don't know. 4.42. 4.43. Okay. So the LDO basically can't do much. If it's a 5 volt LDO, it's just passing along what's going in. If it's a 4.5 volt LDO, it will still do the same thing. But the upside is that the chip is running a lower voltage, so it will actually accept a 3.3 volt data signal with 5 volt coming in. But now we have to test it with 12 volt and see what the regulator regulates to. If it's 5 volt, they didn't use a smart trick and it's just bad. It's okay, but if it's 4.5 volt, that would actually make it so that you can have a 3.3 volt input signal, and you'd still have 4.5 volt on the data out signal, which is high enough. It's not a perfect 5 volt, but it's a lot better than 3.3 volt, right? So let's see. What are we going to do? We're going to disconnect. Are we going to do this live? Maybe. Oh, there is a diode on the input, so that's good. I need to check what is VCC is the left one. Because there is a diode, I can hook this up at the same time and it won't hurt anything. So now we can disconnect. Oh, I need to disconnect all of this. Okay, sorry. Okay. So now we have my benchtop power supply here. So let's set that to 12 volts, 1 amp. Go. Okay. So now let's see what voltage we're getting. Because before the diode, we see nothing. We see 11.9. Okay, that makes sense. After the diode, we see 11.295. Wow, that's 0.8 volt drop. Okay, that's a lot. But now let's see what the things on the LDO say. This is probably ground. This is input, I would say. And output is 5 volt. Okay. They didn't use any smart trick. They just used a 5 volt LDO, but it's getting 4.4 volt because of the diode. And that makes it 3.3 volt signal compatible for 5 volt LEDs. But if you're using 12 or 24 volt to feed this thing, then it's not, because it needs a 3.5 volt high signal. So, yeah. Interesting. So, a Wago would maybe work if you didn't need additional power, and especially a data signal output from one of the standard boards I make. You can maybe split it up twice, maybe 3 times, but after that, the level shifters just don't have enough power, and it'll start corrupting the data signal, basically. Let me lose this thing. So then you can use such a board. Now, would I ever use this for power? No, because there is 0 fuses on there. Bad. But yeah. Okay, so they didn't use a clever trick. This is not suitable for 3.3 volt data signals. You already need a 5 volt data signal. So a proper level shifter, etc., etc. Now, do we want to blow it up? It could be interesting. Let's do a good test first. Let's reconnect this. And we're going to do this real quick. There. Okay. This still works. Oh, you can't see that. This still works. Now, we could scope it, but I think it'll be fine. So what we'll actually do is we're going to take another one of my bars, and we're going to hook it up after 10 meters of cable, bundled cable, and then we'll see if it still works. I expect it to work fine, because a basic level shifter like that, yeah, it should just work fine. So let's see. Let's take, I don't know, this one. Okay, ground. Let's do VCC. And then that one. There. So, as I showed you already, this is my 10 meter 16 gauge 3-wire bundled cable. The other end of that is over here. And I have a Wago on there. Don't need this for right now. So let's take the LED bar connections and ground, data, and VCC and data. Oh, that one didn't stick. What? Okay, other one. These aren't too great. Okay, good enough. Okay. So now we have one bar directly connected through it and another bar connected through 10 meters of 3-wire bundled cable. Go! Okay. Let's set it to rainbow again. Yeah, that is to be expected. That works perfectly fine. So as far as the functionality goes of taking one data input in, as long as you give it a decent 5 volt signal, that should work fine for 5, 12, and 24 volt. And then you can even have a 10 meter bundled cable on there because it has a 33R resistor, and that also works fine. Okay. So let's test some load. Let's see how hot it gets, right? Okay. So let me disconnect this stuff real quick. Now, should we generate some intelligent load? Or should we generate some dumb load? And I'm kind of feeling like a dumb load kind of day. Let go of my wires. Okay. Exactly, shorting the bar. And let me disconnect this and get it out of the way. We can use that later. I don't need this. I don't need this. But I don't want it to be touching either. Okay. Now, we have this connected. There. We have this connected to my bench power supply. And let's take this cable, which is, I don't know, 16 gauge or something. 16 gauge. Okay, that's a decent sized cable. And let's say we're an idiot. And we connected this VCC terminal to this ground terminal. Oops. Okay, oops. And let's turn on the power. So let's set it to 12 volt and 20 amp. No, can we do 30 amp? Set error. Oh, I'm not allowed to set that much? Oh, right. I can only do 12 amps. Because I have an RD6012. I have a bigger one somewhere else. But yeah. Where is the thermal camera? Oh, pin code. Pin code. Let's see, okay. So we have the thermal camera. Of course, we have our required fire stop. Fire stop. It's now even more over the usage date. It's from 5/2016, so it should still be great at stopping fires. I hope. I don't know. So we have our device here. Let me try and give you a shot. No, there. Yeah, something like that. I don't know. Okay, I'll do the camera linking. Can I do the camera linking still? Let's see if that still works. Start now. No thanks. Okay. Okay. Fire might stop, yes. Okay, let's set it to infrared. There, okay, now we can see the thing and see the thing. Okay. Well. 12 volt, 12 amps. Go. It's doing 12 amps. Voltage has dropped a lot. Well, my cable is getting warm. Oh, but the input's getting warmer. There's not a lot of watts flowing because the voltage drops down with a pure short circuit. I think it's too much of a short circuit. Down here there's some temperature too. It's not spectacular yet. Oh wait, this isn't plugged in right. The fan is covered? What fan? Yeah, I pushed it in there. Thanks, Killer. I also noticed it. Oh, the wattage is starting to rise, it seems. This isn't very spectacular at all. Yeah, this cable is not very hot. This one is getting warmer, but not by much. Yeah, but it's constant current limiting. I don't know how to turn that off. No mains for some real firework. No, I don't think anything's burning because my bench power supply basically stops itself. Let's try the problem is my bench power supply is like, this is a short. I'm going to stop. And I'm afraid the LRS will do that too. We can try it though. So we can take this out. And we can take my little board here. Or my, my contraption here. And just take one of the power wires directly. So not through the fuse board. Okay. This one should go in a little bit further, I think. No. Okay. So now it's hooked up to the LRS 600-5. So it's able to deliver 100 amps of 5 volt power. The question is if it'll do that, or again, it'll be like, oh, this is a short, so I'm going to stop. It could do that. But let's see. Power. Oh. Okay, nope. Nope. Right, that is what I expected to happen. So let's demonstrate that again. This is an LRS 600-5. It's a 5 volt power supply, and everybody says, oh, 5 volt, it's safe. No fire. But it can deliver 100 amps or 500 watts. And I've hooked it up directly to this power distribution splitter board, which does not have any fuses. Right? Let's turn that on again. Here it goes. Oh, okay. I think that's enough. I'm going to open the door. Hold on. Oh, I can open the window here. That's, yep. So, for anyone who ever tells you that you do not need fuses for 5 volt, I disagree. My lungs disagree too. Wow, it's still 100 degrees here. While it's been off. Ow, okay, yeah. Oh wow, okay, look at what it did to my desk. Or my desk mat. Oh wow, look at this. It actually melted the coating away. That's what I was breathing. The magic smoke stream, yeah. Now, of course, this is a very, how do you call that? This short is very near to this board, right? So this is just to demonstrate that if there is a short, this board won't do anything about it, especially if it's on its own output ports, but also if it's much further away, all the parts in between that are not up to spec for that kind of current, which is basically unlimited with 100 amp power supply, it's just going to burn. Literally. So that's why my boards, like this one here, have fuses so that in the event of a dead short somewhere in the circuit after this board, It also has input fuses, so it doesn't matter if it's before the board. But it'll be limited to 5 or 10 amps. And it'll get very hot very quickly, and then the fuse will pop instead of a wire will burn. That's why the fuses are there. I mean, I hope this demonstration shows you the difference between this kind of board, which is supposedly for power distribution, and it's still 60 degrees. Why I wouldn't advise that even for 5 volt, and I'd advise a board with fuses on the distribution board, so that everything after a 5 amp fuse, if it experiences more than 5 amps in an error condition, the fuse pops, everything is safe. In this case, if I left it longer, it would probably have burned. So yeah. I don't know why this is still so warm. Oh, I know why. Look at the plastic. And the plastic is actually melted. So over here. And over here, the solder mask is gone. Yeah, no protection whatsoever. And that's fine as long as everything is going fine. But then it starts to rain or something else happens, and voila, you are now not happy. Yes, you missed a lot of magic smoke. We I don't know, stripped the paint off of the PCB smoke. Burnt epoxy is super good for you, exactly. Let's see if I can remove this. No, okay. Well, this is a good way of welding your connectors to the board. What the? Ah, okay. Yeah, that's not looking too great. At least the connector... Oh, I was going to say at least the connector didn't melt. That is untrue. The connector definitely started to melt. I mean, let me show you a good one. Those blobs, they do not exist on the good one. On the side there. Interesting. Okay. And this again, I want to reiterate, was 5 volt. This is a 5 volt power supply. Can I show you that? Somewhat. It's going to be a bit difficult. Oh, all kinds of wires everywhere. There. LRS 600-5. And it'll do 100 watt output because I'm in... or 100 amp output because I'm in Europe. So, for... go away. I'm in 230 volts, but even America, it'll also do 100 amps. Yeah, anyway. Okay, let's dismantle this. That's gonna leave a smell in my lungs. So this isn't a odd power supply to use. We use these a lot. LRS 350s, LRS 450s, 600s. This is the standard power supply a lot of people running LEDs use. And this does not do OCP for short circuit. So if you hook this up to something that does not have a fuse, you risk burning down your complete house. You don't power your Chinesium with a 100... Why not? I just did. Well, this board is now probably done. I want my wire back, though. Can I still get my wire back? Oh, I think I can. Oh, oh, this was also silicone wire, so that's probably why it held up. But it was only 16 gauge. It's not some exotic wire. Well, silicone, but, you know. I guess I can throw this away now. Because, yeah. I don't think I'll be using it anymore. Do we want to see the underside? We want to see the underside. I don't believe it has a current rating. Let me check. No, it just says signal amplifier 5 to 24 volt, 5 volt TTL. Yeah. Yeah, so they both basically have ground here all in the... Oh, wait. They have ground all here in the middle, so that has a huge plane. But then VCC comes in here and distributes like that and like that. And, well, the weakest link was seemingly here. And that's where it started to burn. On the top and the bottom side. Or both, you know. Yeah, okay. I think I'll keep the case. Case is nice. I like the case. Does this go on the outside or the inside? Oh, on the outside. Yeah, I'll put the screws back in it. Show underside PCB. I just did. Nah, because of the place where it burned, I don't think the results will be any different from a different output. Hey Johnny, did you check the last stream? We actually dug up some diff advanced prototypes I made during the stream, which had pink status LEDs. Okay, so I'll keep the case. This can go. Do I want to keep the connectors? No, I have enough connectors. Okay, bye-bye. Let me close the door because it's cold. Okay. Let's take this off. Nice. So, that was device 1 done. The board had a lot of magic smoke in it, for sure. Okay. Next, I'm going to make a prediction and say that this thing also does not have fuses. It has lots of power connectors though. Okay, can we open this up too? Yes. Oh, Aussie Robert, I have lots of connectors in stock. Does it have a 10 amp current rating though? Well, no. If you read this correctly, it can do 10 amps times 5. So, supposedly, this thing will do 50 amps. Okay. Let's see how this goes apart. Oh, there we go. Oh, okay. Interesting. Oh, I like this. Okay, I'm starting. Oh, I think I like this one. Yeah. So let's investigate. I could take the microscope out, but I don't think we need to, because over here, well, this guy here, or these guys here, I believe those to be optocouplers. They are an IM453. IM453. Let's go to here. So IM453. Oh, okay, that didn't give any results. An I2237. An I2237. Okay. Let's add that. I2237. Huh. An IM453. Okay, let's add optocoupler. People have searched for it before. An IL223 is a Darlington output optocoupler. Okay. No, it's not completely what we're looking at. Is it? No, this one has 5 legs, not 6. But let's see for now. Or this is 8 legs actually. Yeah, now it's just finding optocouplers because I put optocoupler in there. Anyway, we can't seem to find that chip. Okay. But I think this is an optocoupler. It then is linked to some resistors. Then there is a tiny small transistor here. That is probably used as a gate driver for the gate from this guy. And then it drives these beefy MOSFETs. Let's see if we can find this MOSFET. It's an. Let me type that in. A 020 N0 BT. A 020 N300. Okay. Do we have which brand is this? I don't recognize the brand. Let's go for the first one. I don't know. Just give me the data sheet. 4-volt drive N channel. Okay. But I don't think this is the right package. I don't think this is it. Nope, wrong package. Wrong package. Jesus. They're on here too. Whatever. That looks better. It's also a 20N00 data sheet. There. on semi. Okay, yeah, that makes sense. 30 volt. Is this thing 24 volt? Yeah, 5 to 24 volt. So that also makes sense. And it's in a D-pack. And I know this is a D-pack housing for the MOSFET. And it's supposedly continuous 20 amps. Pulsed. Yeah, it's not high current. Not that high current. It has a fair on resistance. It's not low on resistance, but it's also not too high. And its gate threshold voltage, which is important, is about 1.6 to 2 volt. Okay, that makes sense. They're probably driving it with 5 volt. And if you drive it with 5 volt, you get this graph here, this one. And that should be fine. That's also almost good enough. But then how are they making 5 volts? Interesting. Because you don't want to put 24 volt on the gate or on this thing. But there's no LDO. Or DC-DC converter or anything like that. There is this little transistor here. So what probably happens is this is the incoming signal. Okay, and the left one is plus. So this is 5, 12, or 24 volt, and these are all negative channels. Those negative channels go into these optocouplers, and that then gets translated using some resistors and a transistor to outputting again on these big MOSFETs, and they probably reverse the signal or invert the signal basically, and the plus for this output comes from this side. So one of the things that's interesting to me is on some of these DC continuity, the inputs are linked to the outputs. And if you're feeding it a different voltage than you want it outputted, let's say you have a 12 volt power supply on this side, but you want to have a 24 volt power supply on that side, the positives shouldn't be linked. So let's figure that out. Okay, beep, beep, beep. Okay, so no link whatsoever between the positive on this side and on this side, although on this side probably the positives are linked. Yeah, right. So if you looked at the cover over here, you can see it. Oh, this is negative. Oh, oops. Okay, so I need this one. Okay, so the positive on the input and the positive on the output aren't linked, and that's why they probably have the optocoupler in between there. But this one is, and this one is. That kind of makes sense, although if they wouldn't have had these linked together, you could have used two different power supplies for this section and for this section, and right now you can't, but that's okay. I mean, sure. Yeah. But at least the input and the output are not linked together. On some of these they are, which is bad. Cool, okay. So yeah, optocoupler in, that separates everything. You can see the positive running here. That feeds this side of the optocouplers. And then after this, it's all linked to the other side. So here's some resistor. So those are all linked to this side. And then there is no electrical connection between the two sides. We can test that a little bit, I guess. So let's test... this pin, yeah. I would have expected this to be positive, but it's not. Yeah, it is. Oh, there's too much resistance. Okay, yeah. But it is positive. Okay, I don't know why they have 1500 ohm resistance between there. They might be using that as a current limiter or a rudimentary voltage drop, I guess. Then these two will have 3000 between them. Maybe other way around. Okay, and this is all okay. And those, so one of the legs gets power from this side, and I guess there can be 5, 12, or 24 volt. It powers these optocouplers on this side. It basically shines an LED inside of this package to the other side, which then gets picked up and put out on this side, which is only linked to over here and not to over here. Yeah. Yeah, that's perfect. Good. I like this. This is basically how I would do it too. Let's unscrew it from the case because I want to see the bottom side. Let's see. I had it like this. Okay, so this is the input side. Nothing here. Good. And then we have... so let's look at the mic like this. Power plus is here and here. So if we flip that, okay. Yeah, so... What? Like that, yeah. Yes. So this is negative, so they have a big negative plane. This is -2, that's fine. And oh, okay, yeah, that's what we're doing. Okay. And then you have positive power coming in here, and they just link it together like that. And so you have a positive output here, and here they do the same thing, link it together like that. So the positives, they might be connected together or they might not be, because I can't really see under the screw terminals. But I would find it illogical to connect that, but we already tested that, and I believe they did, right? So these are connected together. They're not. Oh, what? How is there resistance? Okay. Okay. So there is some kind of trace connecting all the positives on this side. Not on this side of the board, but either internally, probably not, because I think it's a 2-layer. So probably on the top side, they have the positives connected, that when you only put a power supply here, you don't have to put one here. But looking at the traces, I mean, this isn't going to do that. So it has to be on the top side. And, well, there can't really be a lot of trace there, can there? So I would have opted against doing that. Right? Because I think it's dangerous. So people will be like, okay, I'll connect my power supply here, and I can still get a positive output here from the power supply here. So I only have to make one connection to the power supply. But then it has to go through some thin traces that are underneath this screw terminal instead of, well, doing this, right? So I would have left it fully unconnected so that if you only had a power supply here, these terminals would work and these would not. But I guess they made a different decision. And we just saw what can happen. But yeah. So now the question is, how much PWM can it take? Let me screw this back in, because I kind of want to take apart the other one, see if it's the same way, built the same way or very differently. And then we can do some tests. But again, alas, as we kind of probably all suspected. No fuses what to speak of. And we did find some slightly dangerous connections there. Other way around. If you use it properly, nothing bad will happen. But if you think like, oh, I can connect 2 power supplies. No, bad, because they're connected together. You cannot do that. Or you can think, oh, I can connect 1 power supply, but with a single set of cables. No, bad, because then one of the traces will be getting very hot. What you can do, however, is have different voltages on the in and outputs. So that's good. And you know me, I like these connectors. These are good. So I'm going to take apart the other one first. Check that out. And then we're going to give it a test. Okay. Different but the same. Ah, yeah, very different. So, what I was saying before on the other one, how do they regulate the voltage on either side? Or do they use optocouplers that can just use 5, 12, or 24 volt? Oh, so the specs on this one are the same. 5 times 10 amps. Now you only get a single power input on this side, so you're supposed to input 50 amps. I don't know about that. I don't think so. But okay, I mean for 50 amps I use 3 times 10 gauge to not have too much drop. Here you can only connect a single cable. Okay. I don't think that's good design, but sure. And then I think you should derate it. Anyway, we have inputs. No, other way around. Yeah, we have the inputs. So voltage plus, RGB, white and cold white, I guess. So let's first do the same check to see if plus here is connected to plus here. I hope it's not. Plus. It's not. It's open. Yeah. Good. That's good. Okay. I mean, these will also be disconnected. Yeah. Nice. So we see a slightly different arrangement here. They decided to... They also have optocouplers. And they have some diodes in there to give you some extra protection for the signal not making it through. They do have an LDO here. So whatever is coming in is getting down converted to feed these optocouplers, it seems, because there's a trace. There's a trace coming from here through the capacitor over to here, and it goes all along here to feed those optocouplers, I think. And then there's an output here, output here, output here, output here. Okay, yeah, that's good. And you have, okay. They have a status LED. The other one didn't have a status LED. Okay. Now, this one says it's 12 to 24 volt. Okay. That is probably because they need a minimum voltage to down convert for the optocouplers. The other one just has different type of optocoupler. These are 35 volt rated. So that's okay for 24 volt. That's fine. And then on the output side, the other one had transistors driving the MOSFETs. So they could probably drive it with a higher voltage and slam open the gate and stuff like that. This one does not. This one has the gate of the MOSFET directly linked to the optocoupler, it seems. there is a pull down resistor there. So everything is off by default, and then it gets turned on by the optocoupler. But instead of using very high power MOSFETs, they decided to double up, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have 5 channels. So they double up the amount of MOSFETs per channel. And you can do that with MOSFETs. That's fine. So you can double the power rating and spread the heat and things like that. And these are MOS. Let me type that in again. Oh. No. Okay. Where's my browser? MOS CMD 3090L. 3090L. CMD 3090. Okay. Let's go here and go here. Oh, there's a PDF here. Good. Ah, wow, okay. This MOSFET actually has a much lower RDS on, so it has less resistance, so it'll get less hot while transferring the same amount of power. That's good. It's 30 volt rated. Well, it's max 24 volts, so that's fine. It comes in TOE 252. That is this package. The other one had the power pack, so they were much bigger. Super low gate charge. Okay, interesting. They can do a continuous current of 90 amps. Of course, if you actually do that, you're going to require a huge heatsink, and it's basically not possible. And they probably tested it, actually, and decided, okay, let's double up on the MOSFETs. It's better to buy 2 cheap MOSFETs than buy 1 big one. I guess in their case, I don't know. The gate voltage is also nice and low. That's fine. So if they're making 5 volts, this is the 6 volt line. And this is the 4.5 volt line. So the 5 volt line will probably end up here somewhere. So that's okay for the on characteristics. Yeah, this one, this one, you can switch this pretty fast. That's no problem. I mean, this is without a gate driver, so I can't imagine the optocoupler is able to provide a lot of charge current, where on the other side you had a tiny transistor providing the charge current, so that could probably provide a lot more. Do I still have that open? Data sheet. Oh, this one also didn't need a lot of charge current. Okay. Yeah, and it can switch fast enough. Yeah. So this one is also pretty decent from a design perspective. I mean, yeah. Hey, Dave. Yeah, I think this could work just fine. Let's see what kind of resistor they have on the gate. Oh, that's a 10K. Okay. Yeah. So let's see what kind of optocoupler they have. Maybe we can find it on this one. It's always so hard to read. I can almost make it out, but then not completely. The B2301. Yeah. B2301. Let's check that. It is not a compact tractor. B2301, okay. It's not a step-up DC-DC converter. Okay, let's see if I can find something else. 817B. I guess I should have taken the microscope out. Yeah, okay. This is it. That looks, well, it's an SMD package, but that's close enough. Photo coupler. Okay, sure. Okay, 817, sure. Ah, okay, they have different packages. I think 817 is a generic term for an optocoupler, though. Let's see what it does. Okay, packaging. Okay. So it can do 50 milliamps. That's not a lot, but it's comparable to a GPIO pin on a microcontroller. So that's okay. It can take 6 volts reverse. Collector emitter voltage. Okay, so it will do... Okay. Yeah, this is a box standard optocoupler. And as I said, they likely have a 5 volt LDO here, providing 5 volt for the optocoupler, and then also driving the gate with 5 volt. And that looks perfectly within specifications. Yeah. And then having 2 MOSFETs is just for extra power handling and efficiency. I think this will also work great. Have you missed any smoke or flames? Yes, you have. Lots of smoke. I still feel the smoke. So let's put this one back together also. And then let's prepare a controller and play around with some different PWM frequencies to see what happens. Do we still have time? Yeah, we're at 1 hour 50 minutes. Okay. Well, I just demonstrated what happens if your box doesn't have fuses. We're not going to do that again. The result was pretty clear. Okay. Let me get all of this set up. Do I need the scope? Yes, I do need the scope at some point. Don't need this. No, I do need this. I don't need this. Okay. So I can pull that out. Okay, let's get a... I guess we could use an AN Penta Mini. Well, the AN Penta Mini looks really big like that. There. So we have an AN Penta Mini. This is one of my custom LED controllers, which we can program with ESP Home to run at any PWM frequency we'd like. So that's easy. I just need some terminals. I have an orange one here. Oh, I have a black one here. No. Ah, okay. Oh, this is another one. Okay, well, whatever. I'll use... I don't have the right terminals here. That's fine. I'll use orange for power. for positive, and I'll use blue for negative. I need an antenna. I should have some antennas here. Yep. Now this is a controller that's on my desk. That often means it's been messed with. Might not be fully functional. Ow. But you never know. I stabbed something, but I don't know what. Okay, I need to convert this, my bench power supply, to 2 wires. Oh, but I later also need power for this guy, huh? Wow. What happened? Have you ever had that you have like a very thin metal or some kind of splinter in your finger and it just hurts like crap for some reason? It's almost impossible to see. I generally take a piece of tape and try to pull it out of there. There. Probably some metal shaving or a hair from a cable that was still left on my desk. So, how am I going to do this? Oh, I can use a separate power supply for the AM Penta Mini. I should have one, I think. Yes. There. And then we can use the bench power supply for the big boxes. Let's do a quick measurement if this is hooked up correctly. DC. Yes, it's hooked up correctly. Positive on the right side. Good. So I can plug this in here. I got a microscope to detect that splinter. Yeah, that's true. I actually do that sometimes. Okay. I want to program this with ESP Home. But that's going to take some tinkering. Because I need to log into my testing ESP Home. Oh god, I have no idea what my password is. It's not that, it seems. Oh, found it. And let's see, devices. Now I need to copy the configuration from one of my production boards. Add-ons, ESP Home. I'll show you in a minute. Hold on. So let's see here. Test. Let me double check if there's no passwords. I don't think so. Yeah, I think we're good. So let me join it to this window. No. Okay, so we have an ESP home configuration. Now I still need to look up some things in my test home assistant, like passwords. Hold on. Okay, I think those are there. Okay, let's try this. Okay, so test AM Penta Mini, and the rest should be okay. So we have some buttons configured. Okay, we have a restart switch. We're measuring the internal temperature. And then we have the LED outputs defined. And normally I run these at around 20 kilohertz, as you can see. And then we have the lights for in-home assistant. Do we have the web server enabled? Because that would be easy. Web server, okay. And we have the web server enabled. Okay, let's make an install file. Manual download. Yeah, so some of these amplifiers are bad in that sense, TS Productions, that they indeed feed back the voltage you connect on the other side. That's horrible because people try to connect ESPs directly to them. Yeah, well, that's not going to work then, right? So I'm just compiling a firmware for the AN Penta Mini for ESP Home. And then I think we can just use the web page to test it. So let's see if I can actually... No, this plug won't... Oh, this will fit. Yeah. Compiling. I guess it's time for the second drink, huh? Coca-Cola Zero Sugar Lima. Okay. Blah, blah, blah. So I want the ESP Home flasher in a new tab, and then I want a modern format, and Chrome always needs me to tell it to keep that firmware file. I don't know why. I should be able to connect. Yep, there it is. I know you can't see that, but it's okay. I selected it, so I now choose install, test AN Penta Mini, install. Okay. Okay, installation completed. So now it should reboot. So let me reboot it. Just on USB for now. Let me see if it asks for an IP. It does. 10.24.1.128. Let me see if I can reach that. 10.24.1.128. I can. So now that... Oh, come on, Windows. Looks like this. So we have the internal temperature sensor, uptime sensor, Wi-Fi sensor, the button states, and we have the 5 LED channels and the reset button. So we can control the AN Penta Mini. Now I just need to add it into the DNS. No. I can actually edit. So I now know the IP address. I can go back to ESP home and I can say, what was it again? Use underscore address is that. No, not that. So that way I don't have to make a DNS entry. It'll try and use this address to connect to it, because I now know that this address is connected. So let's try that. Hit install and update wirelessly. And it should connect to that IP instead of trying to find it in DNS. What? Invalid YAML syntax. Okay. 18 and 20. Oh. Oh, okay, sorry. I hate YAML. This okay? Mister, I know it's wrong, but I'm not going to tell you. There. So let's try that real quick if that works. Connecting to 10.24.1.128. So now it doesn't connect to DNS anymore. It'll just use that address because I told it in the configuration file to use that address. So we'll be able to OTA updates to that. Good. So then we're ready for testing. So we can disconnect USB. We're going to run the controller off of that white little power supply I just showed you. Okay. And I guess we need to connect an LED strip, which then connects to this thing after that, like that, and then connects to another LED strip. Okay. Oh. Oh no, I rolled over my beautiful cable. Okay. Let's see, LED strip. What do I want? Let me get something. Hold on. I have some 1 meter testing samples, but I don't think. Yeah, those don't have a connector on the other side, right? And these are my color testing samples from Oxmer. But I don't think, yeah, those also all don't have an output solder to them, so I won't be able to use those. This one, come on. I don't think this one is going to work either. What did I do here? Oh, I think this was my 48 volt experiment. Oh, never mind that. I don't know. Whatever. Oh, this might work. What is this? No, this is wrong. These should work. But do these have wires on the other side? So these are from Gree LEDs, and they are CRI 95 CCT. That's fine. We can play with some CCT. Let me get the wires. And I think they're 240 LEDs a meter. But the question is, do they have wires on the other side? And I don't, looking at the spool like this, I don't think there's wires there. So that's not going to work. Well, this is the same thing, so... What's this? Nope. This is some carb strip. Again, only wires on a single side. Nope. No wires. Damn it. What's this? No wires. Oh wait, there is wires. Yep, okay. We can just use this. What is this? DC 24 volt. And it looks like a CCT strip, 2 whites, but it has connectors on this side and connectors on this side. But why does it have... What? Look, there's 2 LEDs. There's 4 wires. What? But there's only 3 pads. What is this 4th wire? Confusing. Can't use that. I don't know. Okay, candidate. Let's look at what's in here. Ah, perfect. Some cheap ass warm white will do. I don't know what's in here. Nope, no wires. A database of all my parts. No, I tried to just remember it. Okay. Let's put this back. And let's use some of this. An optical recognition system. Yes, exactly. Oh, let's then go back. Now, I do actually have a fairly decent organization system, and I try to label things, so that way I know what's what, kind of. Okay. So, how are we going to do this? We are going to connect the cheap-ass 24-volt warm white. I guess we should unroll it, huh? Okay. There. And then we're going to connect that to some GREE 24 volt 3000K, so it's also 24 volt, but it's CRI 90, so that's also fairly cheap strip. But let's unroll it to, well, okay, let's put that over here. Then we take the cheap ass stuff, we wire that into our AN Penta Mini. We need to strip that a little bit more. Okay. There. So now our cheap ass strip is wired up, but we ran into a problem and we need more, and well, even though this thing does 10 amps, we can't do it for some reason. So we're going to take this guy and we're going to wire that up to plus. And whatever, I think it's cold white, I don't know. For now it's cold white. So plus. And this one. And then on the output side, we're going to take my bench power supply, wire that up to the power output. And take this strip and wire, come on, that up to the positive here. And again, the C. Okay. Good, good. So first we're going to turn on this guy. No, wait. First we're going to put on the safety glasses. There. Then we're going to turn on this guy. This guy has fuses though, so that's going to be fine. Then it's going to be powering this thing on the input, I think. But we won't have any output because our bench power supply will still be off. And then later we'll turn on the bench power supply too. Safety first, yes. Nothing happens. Why not? Oh wait, I know why not. You idiot. Because I didn't turn anything on. I think it's LED 1? No. No? No. 2? No. 5? Yeah. Okay. Can you see that? Yes. Okay. Yeah, you can see that. Okay. So we have our strip working, and it's doing 20 kilohertz, or about 20 kilohertz. So even on camera, we get nice smooth fading. Oh, cheap-ass flickering from the cheap-ass LED strip. Let me make this a bit like that, so otherwise I can't see it. Yeah, that seems to be working nicely. Let's go full power. How much power is that? 56 watts. Okay, that's a 2 amp adapter with 24 volt. Okay, let's leave it at 50%. There. Nice. So we have confirmed that the AN Penta Mini is working great. Now we're going to be a bitch and we're going to add a scope to the mix. Ugh. Let's turn on the scope. And I'm going to try and find a way so that you can also see the scope. Oh man, my desk is such a mess. Okay. There. And I guess okay, there, I think. Okay, let's go to the bigger screen there, like that. The multimeter is not in the way, so that's fine. Let's connect it to over here. Now it's always a bit precarious measuring PWM strip because you're actually pulsing the ground. So when ground disappears, well, what are you measuring? So I'm going to take a little piece of wire. This one, for instance. And in this case, we're going to do things in reverse. We're going to say that ground is the positive side. Oh yeah, I had to spend an hour cleaning up those cables. It was fun though. So we're going to add a little wire here. And then we're going to basically say for a quick and dirty measurement, Our ground is our positive, and our LED channel is our negative. So now let's hit auto. And we should get a nice waveform. Yep. So, okay. So let's vary the brightness a little bit. And while I do that, you can actually see that the shape on the oscilloscope changes. Right? Now, you have to remember, this is in reverse. Okay? So basically, the bottom level is on, and the top level is off. Right? So when it's fully off, this is our 0 line, because we're measuring in reverse. So let's turn it on a little bit. Okay, that doesn't matter. And when I turn it on a lot, you can see that this is the on line, and yeah. You can, of course, inverse a scope channel as well. Yeah, I guess I could. How do I do that? I don't actually know. I've done it before. Probe. Coupling DC. No, that's fine. I don't actually remember how I did that. Well, for this example, I don't think it matters. Unless you know on this scope how to do that, Guido. Anyway, we're getting a nice PWM. And if you look at the numbers... well, you can't. Damn it. Hold on. If you look at the numbers for... let's clear it. There. Our current frequency is 9.53 kilohertz. So our PWM is coming through nice and perfectly, and our scope is recognizing our PWM. Our average voltage is like 20 volts, and if I lower that, sure, it goes down, and if I make it more, it goes up. So this is all working perfectly. Great PWM dimmer. I don't know, I just want to show off the input to me. Let me get myself a little bit more room. I think you'll still be able to see like this. So now we are going to enable the bench power supply. Let's set it to 24 volts and let's give it, I don't know, 1 amp. Go. Okay. So now we also have output on this one, and in theory it should mimic. Okay, I need to give it more power. I set 5. Okay, it's getting 5 amps. Oh. In theory, it should mimic whatever this side does. So let's turn it on to slope, little brightness. Okay, but now let's scope this side. I guess I need another wire. Hold on. Wire on the positive side. There. And it'll be interesting to see how well it mimics the PWM frequency, basically. It doesn't look great. Let's give it a little bit more power. That's not right. Huh? Hold on. Well, at least it's mimicking... It seems to be mimicking the frequency okay, 9.53 kilohertz. But the voltage scale seems different. And if we look at the fading, it's kind of confused sometimes. Like if I turn this on, it goes, eh. But it's not too bad, actually. I didn't think it would do that. Oh. I'd say I think this is actually usable. Yeah, can you? Yeah, I don't actually know where my other probes are. That would have been a good thing. I'll look for it just for a minute. Hold on. Because that is a good point. I should use a second probe. Whoa. But where, oh where would that be? Over here? Yes. Good. Okay, let's go this channel. So let's move this one back to the first one. And then we're going to use this one over here. I guess I'll hold them in place for now. Let's hit auto setup real quick. Oh, I need to enable the second channel, I think. Right, okay. So, I didn't put my headphones on, that's okay. Let's give it a little bit of power. Yeah, for some reason the output is shifted over on the output side. So the purple one is the output side and the yellow one is the input side. So this one this one goes down to not sure why that is. At least we're seeing the same frequency. Yeah, exactly, Guido. But this one's currently at a peak-to-peak of 20 volt. And I can't really see, right? That's still the yellow. Oh. Eh? I don't use this scope often enough with... oh, invert. Why is there invert now and there wasn't before? Never mind. Auto. Oh, it turned off invert. One moment, please. Yeah. 1, invert. 2, invert. No. Let's give a little bit more power. Is the scale the same? No. I'm having a hard time matching up the scales. So this one is set to 200 millivolts, and this one is set to... Oh, okay. Oh, it shouldn't be set to 200 millivolts. Oh, wait, is the probe maybe in a different sensitivity? Yeah, okay, got it. The probe was set to a different sensitivity. There, okay, that makes a lot more sense. Now we need to invert them again. Invert, invert, and let's move this down. Let's move this down. There. So, for some reason, the outputs are very different, but they should now match and line up. We're in the same scale now. They're both 5-volt division. But for some reason, the output is transposed differently. I'm not sure why. Because even fully on, they're not aligned. So now they're both aligned, right? They're both at 24 volt. But you can already see that the accuracy is very different. Because even though the input isn't at full power yet, the output already is. See that? So the dimming granularity is very different, it seems. Let's go really low. Yeah, I can still see these being on, while these are off. So let's try something. Let's go into ESP Home. And let's lower the frequency to 1 kilohertz. And let's see if it works better then. Install wireless. I don't need the glasses anymore. Okay, let's go back there. Let's turn this off, turn this on, refresh. Okay. That already looks a lot more similar. Okay, I need to zoom out. Because we're doing way longer pulses now, so I need to zoom out the scope. Yeah, but this now seems to be tracking a lot better. Right, so even when we're at, I don't know what value we are, but close to the maximum, the output is now tracking the input just fine. And if we go halfway, yeah, also lower down, it tracks a lot better now. Yeah, okay. So it doesn't look like this solution is designed for high-speed PWM. No, of course, Guido, but I'm kind of evaluating these if they could be used together with a Quinled analog dimmer. And, well, those generally run at 20,000 kilohertz, or 20 kilohertz, and this one clearly can't do that. So let's go the other route, and let's change it to... I don't know. Nope. Let's do 60,000 hertz. I hate that this menu doesn't have paste. It's so stupid. Oh. Now the AN Penta Mini is somewhat limited in this regard, or a little bit more limited than the full-blown ASP32, which is used in the AN Penta Plus and Deca. Coming soon still, we're kind of stuck still, but I'm hoping to get that resolved next week. Okay. So let's scope that again. Oh. Oh wow. The output side is flickering, I feel like. So let's zoom that in. Yeah, it doesn't know what to do with that at all. So mine still has a decent output. Yeah. I guess it kind of works. Yeah, it feels like this one is flickering in my eyes, but I can't really quantify it. But if you look at the scope, I mean, that's not a nice PWM form there. Hold on, let me. I mean, what's going on? Oh, sorry. There. So let's see if we can identify. So the input frequency it can identify as 60 kilohertz, so that seems to be working okay. Is it measuring that one now? No. How do I get the info for this one? Source channel 2. So let's see if we can get the input. Oh wait, it's worse than we thought. It's not getting it at all. It's not getting this. It only did it. Oh no! What? Yeah, no, it's horribly confused. It has no clue what's going on. It only did it because it was being coupled through my probes. Right? So this one has a good waveform, or somewhat good waveform, right? This one has no clue whatsoever anymore. And it also says, what dimming frequency are we using? None. We don't know. Confusing. It's visibly flickering. And I guess if we turn it up... Yeah, it's not PWMing anymore. No, it's thoroughly confused. So now, even... Basically what we saw before, this range here, until this range here, just doesn't do anything anymore. You can see it on the scope. Now it's starting to react a little bit somehow. Yeah, no. Yeah, exactly, Guido. So let's test my dimmer. It should be able to do that okay. It's not designed for those high frequencies, but, you know. Or it is kind of designed for those high frequencies, but I don't expect people to generally run at those frequencies. But as you can see here, that works fine. Yeah, that's nice. So let's see if it can... Yeah, it can detect the frequency just fine. Oh, wait. Sorry. Yeah. Okay. Okay. So... Wow, it's really confused. Okay, so this one is okay, but it's not high speed, I would say. Right? And it's kind of to be expected. So let's disconnect all that real quick. And connect the other one, because the other one says it's high speed. But what is high speed? Do you know? Do I know? I don't know. I mean, they don't state what it actually is. They just say high speed. Well, I can say my car goes ultra speed, but then just not tell you what that is. So, we do the input side again. We have, let's do this one, doesn't matter. Where's my little green wire? What? Oh, over here. Oh. Ludicrous speed, exactly. As long as there's no definition for what that is, it did it. Okay, and then let's add some power here. There. Let's add the LED strip. And I'm going to do it the wrong way. I'm not going to have a power supply here. There. Okay. And let's turn this on. Exactly, yeah, that shouldn't be needed. Okay, currently we're measuring nothing. Let's refresh this page, because we can turn this side on. There. That is still at 60 kilohertz, but that's okay. And now let's turn the bench power supply on. Did I do something wrong? It's drawing 0.72 watts. Oh, wait, I used the wrong terminals, I think. Well, these are linked together, so that shouldn't matter. But we're not getting any output. Okay, I'll move this one to the right positive terminal, as we determined before. Or the correct one, I guess. There, and... Come on. Okay, let's see if that works better. So let's turn on power supply again. Nope, 0.71 watts being drawn. We have an input, but it's not registering. That's more power. Nope. Oh, yeah, wait, it's doing something. Oh, it's doing something. Okay. Oh, but it's, again, thoroughly confused. Yeah, no. It's doing, I mean, what the hell is it even doing? So it only turns on halfway. Right? So we have this here. This is basically off, it thinks. This is doing, maybe doing a little bit. And then over here, it starts doing something. But it's still a curve which it shouldn't be. Yeah, that's bad. That's bad. Okay. Fine. Whatever, let's leave it all on. Let's go back to ESP Home. Edit. And let's set it to... We'll do the 1000 Hertz channel first to see if it actually works. Save, install, wirelessly. Yeah, wait, no, I don't know if that's not fair or not, because this is a high-speed amplifier. I think 60 kilohertz is high speed. So, I mean, what? Okay. Let's go here. Let's give it a little bit of juice. Oh, wow, it's still not really following. So this is like, nope. And over here it starts doing something. But I mean, do I need to reposition this? No, this isn't my fault, is it? No, no. What is it even doing? Okay, let's go half brightness. Yeah, okay. Yeah, okay, now it's MOSFETting. Wow, it's actually MOSFETting. Woo! How do I switch the trigger on the scope again? No, it's on 2, so it should be working. Wow, that PWM noise. Jesus. Okay. Is this... Okay. Okay, so... It kind of works. Okay, whatever. Hold on. Yeah, so at 1,000 hertz, you could say... Wait, okay, yeah. At 1,000 hertz, you could say it's working, except that if we go halfway... it's still detecting, Oh, okay. That's okay. No, I mean, at this rate, it's working. Then again, if I just have this probe... But then again, the trigger is probably on the other probe, right? How do I set up the trigger for... source, channel 2, trigger at limit, okay. There, okay. So I fixed the trigger for channel 2. Okay. I mean, yeah, that works. That works. Later, Guido. Sure. So for 1 kilohertz, I'll say this works. But as I said, we normally run our controllers at around 20. So the last thing we're going to do is switch back to 20 kilohertz, which we normally run, which works great. Edit. Save, install, wirelessly, go. And let's see if we can do 20 kilohertz, which I would expect, but I don't think it'll do it. And that will mean that these LED amplifiers are not suited when you want to use a decent PWM frequency. So let's see over here. Yeah, I can already see it. So, okay, let me show you this view. You can see that the strip is lit up. And if I scope this side, you can see PWM happening. Okay, I need to trigger on channel 1. Right, so you see the PWM happening. But on channel 2, there's nothing. And that's because the amplifier just doesn't understand something's coming in. So let's raise that. Now the amplifier catches up. And it starts doing something. But no. Nope. Yeah, no. Sun brightness step there. Either way, it turns off. Trigger 2. Yeah, that's not great. So basically this one is still this bright, and that one's off. This is halfway. I mean, yeah, never mind. Okay. That is clear as day. These amplifiers are not suitable for high frequency PWM like we use with the Quinled LED boards. So, even though my AN Pentamini here can run 20 kilohertz just fine, these amplifiers, even though it says high speed, certainly cannot. It doesn't understand the input anymore. It's very choppy, doesn't turn on in the lower ranges, goes very bright in the high ranges when it shouldn't yet. I would not recommend. But that's why I buy these things, and then I test them like this with you guys to know if I should be able to recommend these or not. Because construction wise, they're okay. They're kind of the same way I would build them too. But they're just not suitable if you want to have anything above a kilohertz of PWM, maybe 2, right? So that means I basically cannot recommend it to people buying the Quinled analog controllers, because those generally want to run higher than 1 kilohertz PWM, which I think is pretty low. And we tested 2 of these, which were built differently, right? But both of them failed in the same way. So, I think that... I blew out the microphone there. I think that is a pretty clear conclusion. There's still 60 people here, but there's nobody talking. What? Everyone has gone quiet. What is going on? Should we be quiet? Should people be whispering? I don't know. Let's spool this back up. Is my chat stuck? No. Oh, okay. Chris is still here. More ASMR, please. Yes, Iman, they are in production still. I'm waiting for them to come out of production and to distribute to where I'm going to sell them. And then I'm hoping to still have that done before the end of the year. Everybody busy doing LED stuff, yes. Any updates on the AN Pentadeca? Yeah, so AN Pentadeca and AN Penta Plus have been kind of stuck at the gate. The hardware is done and available, but we're stuck on firmware and testing procedures and things like that. I'm hoping to work that out next week. So with a little bit of luck, we might be able to launch them next week, or at least the Plus. But yeah, that's basically where it's at. Cut that off, because otherwise I'm going to short circuit something at some point. Any plans on doing some updates and testing of analog strips? Still the same plans, I just haven't gotten to it yet. And I want to do that after the analog strips are out, which should be soon. So I'm hoping to maybe spend January and February revamping the analog side of the website, including analog strip tests, things like that. So let's try and roll this up. Draadstaal is thinking of printing a new giant LED cube as large as bamboo can print. Well, that'd be cool. Okay, well this LED strip lives to shine another day. Where's the bag? The cheap ass 24 volt warm light. I was wondering on live streams where the hell the power cable of those 4 strips behind you is coming from. Oh, well, behind me here there is a Quinled Dig Quad prototype which actually had pluggable connectors, but I decided against it at that time because they would get too hot with actually driving 10 amps through them. On the Power 5 I somewhat solved that and I used a different brand, but that's besides the point. So these go up, and I can show you a little bit. Hold on. Oh no. Hold on, guys. There. Those go up, so there, and then they run across the closet, and I had some clips there, but those have kind of fallen off and not. And then they go down there, and then they go there, and there is a 12 volt power supply, because they're WS2815s, stuck to there, which is linked to a power plug that is this guy here. This one here. And now you can see the actual mess on my desk. It's, yeah, there's a lot of mess here. But, you know, that's life. There's work being done. Let me try and get you back there again. Like that? No. Like that. Yes. Good. Years-long mystery solved. Yeah. Oh, you liked my Dawa camera test before. Yeah. We might get some new stuff again in the future. If the things with the new house proceed, I will probably be doing a little bit of IP camera stuff again. I don't think I want to focus the channel on it too much, but who knows? Who knows? So let me see why now it feels higher than before. That's okay. Now it's crooked again. Hold on, hold on. We'll leave it like that for now. There. What did you make me do? A bamboo P1 impulse buy. Oh. Yeah, I have an X1C, and I really like the X1C. It's great. But I hear the other ones are good too, so I don't know, you know. Later, good night, Stefan. That was the secret. How was the background LED strip powered? Exactly. Right? Well, I don't actually have a great other secret for you today. Yeah, that I hope that the AN Penta Plus might come out next week, and the AN Penta Deca isn't far behind it. Otherwise, there's all kinds of stuff in the works, but nothing I can concretely tell you right now. Is the bamboo that much better than Creality? It depends. Do you want to mess with the printer? Then the Creality is better. Or if you just want to print, then get a bamboo. You're on a plane flying home watching, and you can watch this in real time? What? How is that possible? Just print. Then I can advise a Bamboo. Of course, I only had an Ender 3, which was modified and things like that. So maybe the newer Creality stuff is better. I just, the Bamboo works great. So. That is correct, Henrik. So the WS2811 protocol is a fixed speed. So if you have 100 LEDs, it'll do like 333 FPS per LED or diode or whatever. And thus, if you have 200, it'll do half that. And if you have 300, it'll do a third that. And if you have 600, at some point, you're going to reach a frequency where you don't want to add more. So there's an article on my website, this guy, which explains that. Paste. And so basically, if you look at the table with 600 LEDs, you're down to a theoretical max frames per second of 55. And that's where the problem is. If you continue to 1,000 LEDs, that works, that's no problem. But then you're down to 33 FPS for those 1,000 LEDs. And animations and transitions and things like that will start to look much choppier. So that's why we recommend 600 or 5 to 600 for RGBW. That is because of the frame rate dropping if you go over those numbers, and it drops to a visibly choppier experience, basically. But that's why we have a Dig Uno with 2 outputs, and a Dig Quad with 4, and a Dig Octa with 8. You can just spread it over those outputs, and then there's no problem. Or you use some of those Cobb LED strips, which have addressable zones nowadays, and then you run into those limits much less quickly. So yeah, I think this really was the secret, because I don't really have anything great to tell you right now. I do thank you all for hanging out here and sticking around. We've gone over the 3-hour mark again, and there's still 56 people here, so that's awesome. We did a lot of stuff today. We smoked out this board, and we tested it, and the level shifter setup inside, data-wise, that's pretty okay. Power-wise, I personally wouldn't use it. I want it to be fused, and then you can use a Dig Octa or power board or something like that. You can even use it in combination if you really want to. Oh, such as the new Quinled 24 Cobb strip. Yes, yes, it is coming. I'll share more in the Discord this week, I think, but it is coming for sure. I can't tell when yet. So, yeah. And while we looked at the analog amplifiers, 2 of them, high-quality models. These weren't the cheapest one for sure. And although the construction is okay, these, they don't have continuance. They don't have the pluses on both sides connected, so that's good. They use optocouplers, that's good. But only when using low-frequency PWM. If you go higher frequency, it doesn't work that great. So, yeah. I don't know, Iman, because I can't make like 100,000 strips. They're not going to be cheap. They're going to be unique, but yeah, we'll see. We'll see. No problem, Henrik. No problem. Okay. I'm gonna sign off. I thank you all very much for watching. As I said, it's great having you along in the journey. I can do these tests on my own. I often do. But then again, it's fun hanging out with you guys and doing them while you're here and maybe blowing some stuff up. Thanks for watching, and catch you in the next video, next live stream, in the comments or on the Discord server. Bye-bye.